This video and the next will show you how to use computer graphics to visualize data to understand a scientific or engineering concept. We'll consider an example of implementing greatest gradient descent. Greatest gradient descent is often used in deep learning or machine learning, which is a branch of AI, artificial intelligence. In the real world, many physical quantities such as the cost of a product or service depends on a number of parameters or features. For example, the price of a house depends on the size of it, the number of rooms, and how old the house is, etc. Or another example, the price of a stock depends on the revenue of the company and the earning of the company and some other features. Okay. So we'll model a problem using these features. So we can consider the output, say the cost. Z is a variable that depends on a number of parameters, x. So x is a set that contains n parameters, x1, x2, x3, blah, blah, up to n. So now, given a set of parameters, we want to predict its output. We can learn from some sample data, say m data samples. Now, be careful of this m and this n. They are different. This n is the number of features, and this m is the number of data samples. So we denote these data samples using this notation. So x1 consists of parameters x11 or variables, values, x21 blah blah xn1, and the output value is z1, and x2 consists of the values of these parameters x12, x22, xn2, and their output is z2, and so on. And xm is x1m, x2m, blah blah, xnm, and the output is zm. Okay. So for the jth data, we have the input, which is x denoted by xj, and the output denoted by zj. So now, given an arbitrary input, we want to predict or ask what's the output. Say for example, for this kind of house with 3 bedrooms and 1,000 square feet, and built in 1980, what's the cost of it? We can do this by assuming a hypothesis, say x theta, which depends on x. And we assume that this hypothesis can be expressed in this form: theta 0 plus theta 1 x1 plus theta 2 x2 plus blah blah theta n xn, or written in the math form, sum from I equals 0 to n theta I xi. We define x0 to be 1. So what we need to do is to find the constants, theta 0, theta 1, theta 2. So we call this theta, which is a set of theta 0, theta 1 up to theta n, to n plus 1 values. And with these values, we want to minimize the error between the prediction and the actual data. So the error can be expressed as j theta, sometimes referred to as Jacobian. It is equal to 1/2 sum over all the data from j equals 1 to m, x theta xj minus Cj square. So to find this x sub 0, theta sub 0, theta 1, theta n, a popular method to do this is the gradient descent, this spelling of gradient here. So the algorithm is like this. We start with some theta, say 0, the 0 vector, and then we iterate theta I equals theta I minus alpha partial j theta partial theta I. That means the differentiate j, say the error with respect to a certain theta I. Then we multiply this by the alpha, the learning rate, and so this differentiation is the gradient of j along theta I. So by iterate along this direction, then eventually we'll obtain the optimal theta I. So if we do the math, carry out the differentiation, then we obtain this formula. So theta I minus alpha sum over j equals 1 to m x theta xj minus cj times xij. We sum over j only for a particular I. So we consider a simple example. In the example, we consider, for example, the price of a stock. That depends on the company's earnings and revenues. So that means we have two features or two parameters. So in this example, n equals 2, and we have one output. So we can represent the data in 3D graphics. And in the example, the earning is x1 and can be represented by x. The revenue is x2, can be represented by y, and the price, the output, is z. So in the 3D graphics, we have x, y, z to represent the inputs x, y, and the output z. So our hypothesis will be given by x theta x equals n equals 2. So we have theta 0 plus theta 1 x1 plus theta 2 x2. And to represent this in 3D graphics, we need some simulated data. So our simulated data will be generated using a random number, and they will be normalized to values between 0 and 1. So that means the x, y, z values are between 0 and 1. And the output is a Gaussian distribution of the inputs given by this formula. Z equals e to the power negative x squared plus y squared. Okay. And now the hypothesis theta x is equal to theta 0 plus theta 1 x plus theta 2 y. So our task is to iterate each of these theta to find the set of values of theta that will convert to or approximate the output values z given the same set values of x, y. And we'll present the implementation in the next video. Thank you. Bye.